Hi there, and welcome to this talk on building deep neural networks in .NET. In this talk, we'll take a deep dive into deep learning and understand how they work from the inside out and see how we can build our own networks using the open source library ML.NET. My name is Alexander Slotte, and I'm a Microsoft MVP based out of Washington, DC. I currently work as a managing consultant for Excella, and I organize the .NET DC meetup group that meets once a month in Friendship Heights. I love speaking and engaging in the community, and I occasionally blog as well on my blog, alexanderslotte.com. So what are we going to talk about today? Well, we're going to start off with some basics of machine learning and understand the general concepts and terminology that we'll need later in this talk. We'll then take a deep dive into deep neural networks and see how they're constructed and built and how they work and what moving parts we have to work with. Using that theoretical knowledge that we have gained, we'll then switch gears and go into the open source library ML.NET and see how we can apply our newfound knowledge building our own networks. To finish things off here, I hope to have enough time to do a proper demo showing you how we can do this using both Jupyter Notebook as well as Visual Studio. So what do I want you to take away from this talk? Well, I want us to fully explore ML.NET and understand how it relates to its Python equivalent, scikit-learn, as well as to Google's flagship within deep learning, Tensorflow. Are they competitors, or are they working towards the same goal? Well, let's find out. Before we dive into the practicalities of using ML.NET to create our own deep learning models, let's take a moment to understand what machine learning really is. As I'm sure you're all aware, you see deep learning and machine learning models all around you every day. You may notice them when you use something like Spotify or Netflix for your recommendation systems. You have face recognition systems being used across the world today. If you talk to Google Home or Siri, you use natural language processing to translate your speech to text and commands that you can execute. One of the more up-and-coming things where AI and machine learning is heavily used today is for cybersecurity, and I am pretty sure we'll see more of that evolving as we go forward. So what is machine learning? Well, machine learning is programming the unprogrammable. And to put that in simpler terms, let's think of you taking a picture of your house, of your pet, for example. Can we program a software application that will detect that this is your house in the picture? Of course we can. We can write a simple program that parses the values of the pixels and then extrapolates a pattern based on those pixel values to understand if this is the color of your house, the shape of your house, the windows that you expect to be seen, and so forth. And that probably will work just fine. But what happens if you take a picture from a different angle, different distance, different lighting, maybe even a different time of year? Well, your software application is going to struggle to determine if that's your house or not, because the pattern is being used to determine that is different. So we need something more general where we can feed it tons of examples to figure out this on its own and not rely so much on our own knowledge. And this is where machine learning comes in and becomes very useful. Machine learning is based on models. To create a model, we feed an algorithm a bunch of known data. We then use math to iterate over data in a process called training, which will yield a model. We can then use the model on unseen data to predict outcomes that we want to understand. The process is iterative, of course, and we'll have to go back and retrain the model once we have new or better data. If we take a closer look on what machine learning really is, it's nothing more than just a function, y of a function of x, where x1, x2, xn are your features or different properties in your data that you can use to predict your desired outcome. In the data science community, we call the answer we're trying to predict the label, while the columns in the data set usually are called the features. To give you a proper example of this, think about predicting house prices in your area, where x1 could be number of bedrooms and bathrooms, for example, the zip code, location of your house, and y is going to be the price prediction that you want to get out. So there are different types of machine learning, and one generally talk about supervised and unsupervised learning as well as reinforcement learning, although there are also examples of other kinds of machine learning types. For this talk, we're going to focus mostly on supervised and unsupervised learning and really dig down into what those things are. When we talk about supervised learning, we generally talk about training a machine learning model by using data that's already labeled. So what do I mean with that? Well, for example, when we talk about the house predicting example, we're going to use data that both have the information about the property you're trying to sell, as well as the historical price that it was sold for. When we talk about image classification, we're going to use a set of images where we already label them if it contains a broccoli or potato or a person or a pet, for example. So we have already labeled data and we can train a model in a supervised fashion. So when it comes to unsupervised learning though, we don't have any labels and we instead want to dig down into the relationships in the data. For example, we can look at customer segmentation and understand if a marketing campaign that works for customer A is going to work for customer B as well by using a 2D or 3D clustering method. We can also look at things like principal component analysis to really boil down multiple dimensions into a smaller dimensional space. And we can also use anomaly detection to better understand sales data and see spikes in financial data or see spikes in our industrial systems to maybe stop an important process before it's too late. Alright, so now we know a bit of the basics of machine learning. Let's switch gears here and really dive into what deep learning is and what it's all about. Under the AI umbrella, we find machine learning to be one of the strongest pillars, and deep learning is a subset of machine learning. And I generally refer to deep learning being machine learning on steroids. So what is deep learning? Well, when we talk about deep learning, we also usually talk about deep neural networks. And what are deep neural networks? Well, deep neural networks is nothing more than something like this schematic right here, where we have layered networks of neurons that are connected to each other in some way or another. Between the neurons, we have something called weights and biases that influence how important a signal for one neuron is to another. Each of these neurons is just an abstraction of linear algebra, and it's just a way to more easily speak about this. Neural networks consist of an input layer, an output layer, and hidden layers. When we talk about deep neural networks, we generally talk about the neural network having more than 2 hidden layers. To make this more understandable, let's look at a practical example. So imagine that we're trying to build a fraud classifier, which is going to try to determine if a transaction is fraudulent or not. And we can, for example, think of this being determined by the type of transaction, the amount we're transferring, as well as the location this transaction is taking place. So how is this working? Well, all of these 3 features are going to be converted to numeric values and then passed into the network. And the network is then going to keep passing these features down the chain by applying weights and biases to each input value. And at the end, the network is going to try to determine if it's fraudulent or not. In this example though, we're using something called supervised learning again, so we know if the value is correct or not. And the network can then calculate how far away it was from the correct value using something called a loss function. When it knows how far away from the correct value it was, it can then use something called backpropagation to go back into the network and adjust its weights and biases so that the input data more strongly correlates with the prediction that it's giving. And by doing this multiple times with multiple data sets in something called epochs, we can then have a network that's more and more fine-tuned to better understand the data that you're sending in, and we will eventually have a fraud classifier that is much more accurate. So how does a neuron really work under the surface? Well, let's take a look, shall we? This schematic here kind of gives you an indication of the simplicity of the math behind it all. All we're doing here is we're taking the input values x1, x2, xn, which for example is the location, the place, and the amount of the transaction, and we're multiplying those with a random weight, w1, w2, and so forth. All of these products are then summed together, and a random bias is added at the end to give the output of the neuron. To add some kind of non-linear functionality to this neural network, we're also applying an activation function that are making sure that our output of the neuron is going to be between 0 and 1. There are multiple types of activation functions, for example sigma functions and ReLU, but those are out of the scope of this discussion at this moment. I do want you to appreciate how simple this is though. One may think that deep neural networks are complicated, and of course they are, but the math behind it all that really is the foundation of it, is actually not that difficult. It's just simple multiplication and summation. To finalize the discussion on neural networks, let's take a look at the 6 building blocks in my view of a good neural network. Well, first of all, we have the neuron, which is just an abstraction of linear algebra. We then have an epoch, which is one pass through the network. So think about an epoch as a training round by using all of the data at hand. And each training round, we of course are going to adjust the weights and biases in the network, which is where we store the knowledge. After each training round, we use something called the loss function to calculate how far away from true value we are. So that's the feedback mechanism that then triggers the backpropagation, which is where we adjust the weights and biases to better fit our data. An optimizer is used during the backpropagation step to understand how we're going to update the weights and biases, and usually we talk about gradient descent here. Activator, again, is just introducing nonlinear behavior in each neuron, and it's trying to normalize the value that is coming out of the neuron between 0 and 1. And we have activators such as ReLU and sigmoid functions to do that. So what types of networks do we have? Well, there are plenty of different types of networks and different architectures, but in this talk we're going to dive into just the 3 big and main ones. The first one being the multi-layer perceptron. And the multi-layer perceptron is something called a feed-forward fully connected network, and we've already kind of discussed that in pretty good detail so far. It's one of the more simpler types of networks, and it's used if you want to create your own kind of custom structures in some ways. The second type of network is called a recurrent neural network, or an RNN. And an RNN is very commonly used into something like a translation at Google Translate, speech to text, and anything really that has to do with time series data. So what is specific with time series data? Well, in any kind of time series data, such as like a language where you're constructing full sentences or predicting stock prices or weather, it is important to realize that the historical data is important. Just take an English sentence, for example. It's difficult to translate a sentence until it's fully complete, because the end may actually affect the beginning. So why do I mention that? Why is it important? Well, it's because in recurrent neural networks, we have that kind of backward feeding mechanism. So it's not only a feed-forward network, but cells also feed back to the previous layer to make sure that not only the input has importance, but also the outcome of the following layer. And finally, we have the last type of neural network called a convolutional neural network, which is heavily used in computer vision. And I'm pretty sure that you've heard the most about this network. I wanted to save this to last because I think it's one of the most interesting types of network. And to the right in the schematic here, you can probably recognize something we talked about before, which is a feed-forward, fully connected network, where each neuron is connected to the next layer and so forth, and we finally have an output layer where we're trying to determine the class, and in this case, truck, car, van, or bicycle, and so forth. But what is interesting here is that the majority of the network is designated for feature learning. And why are we doing something called feature learning when it comes to image recognition and image classification? Well, to understand that better, let's take a look at what an image really is and what it's made up of. We of course have multiple pixels image, and depending on the resolution, we have more or we have less. But an image also consists of multiple color channels, so red, green, and blue, right? And each of these channels have pixels themselves. So in essence, a picture ends up being tens of thousands of hundreds of thousands of features if we treat each pixel as its individual feature. So training and creating a network with so many features is very demanding, and it's very, very slow. So we have a network that trains very slow, and we have a network that will also do its inference very slowly. And that's why we have this feature learning phase, where we're using kind of grid systems, if you will, or filters, to slowly filter down the picture into its most important features. So for example, if we take a picture of a human face, those filters that we apply to the image to downsample it may detect the shapes of the face, or the eyes, or the eyebrows, things that it thinks is important for its feature engineering and feature learning phase. And in the end, it will downsample the image to a much smaller size that we can then feed directly into a feed-forward network that will both train faster as well as infer the result of the picture faster. So now we know what kind of networks we have to deal with here depending on business scenario. How do one go about creating their own? For example, let's say we want to do an image classification example to detect if there's different food types in a picture. Do we have to ourselves go and create that feature learning phase? Or do we have to train it from scratch using thousands of images? Do we have to design and architect that feed-forward type of classification network at the end? How does that all work? Well, fortunately enough, we have something called transfer learning that we can leverage instead of starting completely from scratch. So why is transfer learning important? Well, if you think about the amount of time you need to train a CNN from scratch, we're talking about days or weeks depending on what kind of computer power you have, and we're also talking about thousands, if not 100,000 of pictures of different scenarios you also need to use to get an accurate and good network. For many people, even for many organizations, this is not very feasible because you may not have that amount of pictures or that amount of data that you need to create an accurate model. But we can use something called transfer learning instead to unfreeze certain parts of the network and retrain them specifically, while you leave the rest of the network that has already been trained frozen and unchanged. I usually think about this as myself, for example, trying to recognize people out in the city. If I never met your friends before, I don't know who they are and I don't know their names, but I'm very good at realizing who's a person, who's not a person, right? But if you tell me once or twice that this is John or this is Sarah, I will learn and I will remember that these are your friends and these are their names. The same thing with transfer learning. You take something that is very general and good at a general task and you teach it something very specific using a much less amount of data. And that's why transfer learning is very useful in many cases, because we don't need as much data and we can do it a lot faster than we would if we had to start from scratch. Alright, that's a lot of theory. So let's switch gear here a bit and let's talk about how we can apply our newfound knowledge into machine learning and deep learning by using the open source library ML.net. ML.net is a machine learning library for .NET developers. It's fully open source and cross-platform, so you can contribute PRs and issues and even code yourself on GitHub, and you can run it on Linux, Windows and iOS, whatever platform you desired. The really cool thing about this is it's built for C# and F# developers, meaning that you can train your model in C#, F#, and you can deploy the model as part of your .NET application. For example, you can deploy your model as an Azure function and serve requests that way. You can integrate it seamlessly into your ASP.NET Core application. You can even put it into a desktop application in WPF, or if you want to, even on your phone, as it has offline capabilities. So the cool thing here is that ML.NET is completely offline. It does not need to have any cloud connectivity because the model is just a zip file that you create and you import into your own application. It was initially released in 2018 at MS Build and then put in general availability at MS Build 2019 and has since then really rapidly developed and become a fantastic library for a lot of developers to use. Something that I really enjoy with the library is the model builder, which offers an automatic ML experience where you can just provide the dataset and the library and the framework will then output the model as well as the code that you use to train that model on. As of November this year, we now have more support for deep learning. So as we'll see later here, it supports transfer learning, so retraining existing networks with your own data. And it also takes a steep climb into the data science community as of November last year when it supports Jupyter notebooks with the .NET kernel using .NET Interactive. Jupyter notebooks are really cool and perfect to use for data exploration and summation. For example, if you want to see the relationships of your data in a graph, or if you just want to see the confusion matrix being displayed after you have trained your model and evaluated its performance. So when you train a model using ML.NET, there are certain steps that are repetitive and that you always do, regardless of what kind of ML task you're trying to solve. Regardless if this is classification or if this is a regression problem, you still do these steps. So the first thing you always want to do is load your data into memory, into something called an iData view. The iData view can be loaded from either a file on disk, such as a CSV file or a tab separator file, or you can load it from a SQL server or even from a streaming dataset if you don't have sufficient memory. Once you have your data, you generally want to divide it into a test and a training data set. The test set to be used to evaluate the performance of your model later, and the training set to be used to train your model on. You can also use techniques such as cross-validation if you have a small data set. That's completely up to you. Once you have your data into memory, you do want to append different transformations on your data using a data transformation pipeline. Each transformation is a method chaining call. For example, you may want to replace missing values or null values in your dataset using those kind of transformations. You may also choose to transform literal values in your datasets, such as a text value of a name or a type of car, to a numeric representation that your machine learning model can understand. And you can also do that with tons of different transformations that you'll find in the library. Once you have your data in a correct format that you can use for a model, you want to call the fit method on your model. We'll take the training data set and the algorithm you've chose to use, and it will try to come up with an accurate model for you to have. Once you have a model that has been trained on your data, you can then use one of the available evaluation methods on your model to get reliable metrics. And you can use those metrics to compare with the previous model of yours and see if this one has become better or worse. That will allow you to decide if you want to take another loop in the cycle to train the model using new data, if you want to adjust the algorithm you have picked for your particular task, or for example, if you want to add additional transformations of your data set. But once you have a model that you're happy with, you can call save on that model to save it into the disk, and that will end up being a zip file. The zip file can then be loaded into a production system. For example, you can either deploy it as an Azure function, or you can load it into your ASP.NET Core application using a simple one-line command. You can then create a prediction engine, and using that prediction engine, you can then take input data with the same schema as the schema you used for training your model on to make predictions on unseen data for real-world examples. So awesome! We can do tons of machine learning tasks in ML.NET, but what kind of deep learning can we do in ML.NET? I mentioned earlier that we haven't really seen deep learning support until this fall of 2019. And how far has this library come in supporting the deep learning community? Well, we can do something called image classification using ML.NET. And there's two ways to accomplish that. One way is using transfer learning to take an existing neural network, an architecture, and retraining it on your own image set. For example, we can take an Inception v3 architecture from Google, or we can take a ResNet architecture from Microsoft, and we can freeze most of those layers and retrain some of those layers with your own data set, which will be a lot faster than training it from scratch, as I mentioned earlier. And this is something called transfer learning again. We can also use something called ONNX. ONNX is Open Neural Network Exchange, which is an open standard supported by Microsoft and Google and Facebook that allows a common format between different machine learning libraries. For example, we can train something in ML.NET and export it to ONNX and import it in scikit-learn, or vice versa. So that means we can train a model using, for example, Tensorflow, and export it from Tensorflow and ONNX and import it in ML.NET to be used in our C# application. This obviously opens up the library for tons of different use cases, because we can reuse models that has been trained in other frameworks in our own C#.NET applications in production. Another deep learning task we can do with ML.NET is object detection. Object detection, in my view, is less supported than image classification just because we can't really train our own models using ML.NET. But we can consume models from other frameworks. For example, again, we can use Open Neural Network Exchange to import models trained in TensorFlow or PyTorch into our C# application using this open standard. We can sidestep this a little bit. So we can, for example, use the Azure Custom Vision service to train custom object detection models with our own dataset, and then use Azure Custom Vision to export that model to the Onyx format so we can use it in MLNet. So, yep, there are some ways around this, so we can train a custom model and use it in our own application. But in theory, in practice, we can't necessarily do that. So you have to use an other library or a cloud provider to train your model for object detection, but you can certainly use it in your applications today if you want to get started. For those of you in this talk with some deep learning experience, you may realize that we have quite a big gap here when it comes to deep learning support. We are missing things like natural language processing, we're missing things such as a Keras-like API on top of MLNet to build our own architectures with, let's say, 5 different layers and a width of 32 neurons and so forth. We missed the ability to select our own activators and our own optimizers. We missed that kind of fine-tuning support that you may be used to in the Python community. Not to say that we won't see that in the future in MLNet, but I believe that the current roadmap for the framework is to be more easily used with less verbose syntax to get some of the most common business scenarios up and running quickly. I am very passionate about this library, and I'm really excited to see how this library transforms in the future. And we're still very, very early in the deep learning space for C# developers. Alright, there's a lot of information at once here, and I hope I haven't overwhelmed anyone so far. But we have taken a minute here to dive into machine learning and deep learning. We've seen how neural networks work under the surface. We've seen how weights and biases come together with optimizers and loss functions to form this neural network that learns. And with all of that, I want us to go back to the slide that I showed in the beginning with MLNet and scikit-learn and TensorFlow all coming together as one. How does these libraries relate to each other? Well, as we learned so far, scikit-learn and MLNet are not necessarily competitors, but they are brothers or friends. They're just in different programming languages. We have scikit-learn being part of the Python ecosystem, and we have MLNet being part of the C#net system. So the question is, do I think that MLNet is going to attract Python developers from the scikit community? And my answer to that will be no. I don't think that we will see Python developers transitioning into the net community to start using MLNet. And nor do I think that the framework founders and contributors are envisioning that neither. But I do think that MLNet will enable the larger .NET community to take the step into machine learning and really dare to make their applications smarter by just using simple things like AutoML or build their custom machine learning models from scratch. It is easy to use, it's very quick to get started once you figure out the basics, and I really encourage you all to start looking at that today. So how does MLNet relate to TensorFlow, for example, which is Google's flagship for deep learning? Well, as you learned this talk so far, MLNet uses TensorFlow under the surface to train its deep neural networks. We will see in the demo in just a bit here how we can use TensorFlow to train our models and actually get output from the TensorFlow library in our console, either in Jupyter Notebooks or in Visual Studio. I think it's just really cool. And I really like that MLNet is not trying to create a stronger or better deep learning framework, since TensorFlow is already the go-to network for deep learning. If you want to get started with MLNet today after this talk, I really encourage you to go into either the GitHub repo for MLNet to look at open issues that you can get started with, or the .NET Machine Learning Samples repo, which contains all the community samples. And the community samples repo is just fantastic, because it gives you an idea of how you can apply MLNet in different business scenarios and different ML tasks, such as time series forecasting, classification of different kinds, regression, and also, of course, deep learning scenarios such as object detection or image classification. MLNet also, of course, has official Microsoft documentation, which is good. It doesn't have so much there that you may need to get started, but it's a great resource to get started with. I also have a lot of repos on my own GitHub page with examples, as well as a workshop I give that is either half a day or full day. If you have any questions to me after this talk, definitely feel free to reach out to me on Twitter or LinkedIn or whatever other medium you like, and I'm more than happy to answer your questions. And with that said, I think it's time to dive straight into the code here to see how we can use ML.NET to build our own deep neural networks. So what are we going to try to do today? Well, what I want to try to do today is create a machine learning model that can automatically label images in terms of what product they belong to. For example, let's envision we are a big e-commerce website and company. Let's say Amazon or Walmart or IKEA or what have you. And we have a lot of different images, a lot of different products that we offer our clients. For example, we can offer them clothing, such as shirts and belts and jeans and so forth. But we may also offer them stationaries, such as pens and papers, or something else. And we don't want to hire someone to manually go through all of our products and manually label their product category so that our clients can more easily find them. Especially this is important when we get new inventory and we automatically want this to just appear on our page. Because we know that a manual process may be tedious, it may be expensive, and it may also be error prone. So what do we need to create such a model that can automatically categorize our items into the correct buckets? Well, first of all, we need a lot of data, and we need it to be very diverse. So we need a lot of images of shirts, for example, with different colors and different shapes for male and female from different angles. And we don't want different pictures of belts and so forth. Because we want our machine learning model to be able to determine that, hey, this is actually a belt, even though this is a new brand or a new vendor that is giving us this, and the lighting of the images may be different, or the color of the belt may be different. So a very diverse data set is what we're going to need. Today, we are going to use the data set you see in front of you. It's going to be one that exists in Kaggle, which is a data science competition platform, which has tons of great data sets out there. So I really encourage you all to go and have a look if you haven't already. If you go to their homepage and search for fashion product images, you should be able to locate this data set. You can also find this data set on my GitHub page if you're interested. My GitHub page is aslotte, and the repository where you can find this in is going to be mlnet-jupyter. I encourage you to download the source code that I'll show you today and play around with yourself. The best way to fully understand how something works is to sit down with it yourself and take a few minutes. I believe that you will find it rewarding and hopefully a good learning experience as well. For our example today, we're going to use something called a Jupyter notebook to create and train our model in. We can of course do this in Visual Studio Code or Visual Studio the full IDE as well, but to really kind of immerse into the data science community, we're going to do this example in a real notebook instead. We have support for using Jupyter notebooks as of November last year. We have something called .NET Interactive, which is fantastic with a .NET kernel under the hood here. If you haven't used a Jupyter notebook before, don't worry, it's actually very simple. I use something called Interact, which is a local IDE that you can download and install on your Windows machine or elsewhere. And it allows you to create a notebook and execute the cells independently. But in general, what we're looking at here is just a notebook that has different kinds of cells, as you can see here. In general, they have two kinds of cell. One which is a markdown cell where you can have a documentation, for example, titles or any text that is helpful for your example. And then you can also have code cells, which contains the code you're trying to execute. The cool thing with a notebook is that you don't need to execute all cells at once. You can execute cells one at a time. So for example, loading data into memory, and then following cells to manipulate the data based on that information that you have gained. So when we start building our models in ML.NET, the first thing we want to do is of course define our dependencies to ML.NET, the NuGet package itself. And the way we do that in something like a Jupyter notebook is using the magic keyword !r, as you see in cell 1. $r allows us to define the source of our dependency, which is going to be NuGet, as well as the package name and the version. And we can see here on the first line that we're using Microsoft.ml and the version 1.4. And we also have to import some additional dependencies here for computer vision and image analytics for this package itself. And the last thing we need to do here is also import a distribution of Tensorflow, because as I mentioned earlier during this talk, we are actually using Tensorflow under the surface to train our deep neural network, which I think is just very, very cool. And once we have installed our packages, we can then define our using statements and start using that throughout the application. And if we execute this cell, which I've already done for saving some time here, we'll see that we install our packages that we need and they'll be available for us to use throughout this notebook. So once we have installed our dependencies, the next thing we want to do is load our data into memory. And remember that I mentioned earlier that we can load our data into memory from either a CSV file or data in other ways, or enumerable, or even a SQL database. In our case, we want to load our data through two different sources. Then the first one being a CSV file and the second one being the directory with all the images. The CSV file contains all the metadata about each image, for example which category it belongs to and other things such as article type and base color. The only thing we really care about is the category here, and the reason for that is because we are doing supervised learning and we need our training datasets to be labeled. So in order to actually create a model here, we need to load our images into memory with both the path to the image as well as the category that we have already labeled those images with. So to do that, what we do is we are defining a schema both for the image data, which contains the image path as well as the label, so the category again. And the second thing we are defining is the schema of the CSV file. And what we will be doing here is loading each row of the CSV file into memory, and then based on the ID column in the CSV file, we'll construct a path to that image. And we'll feed that information in to ML.net so that ML.net knows that, hey, here's all the images that you need for your training of the model, and for each image, this is the category that the image is of. So that data loading and that data massaging can be seen right here, where we load a CSV file, all the rows of course, and then parse out that image data class that we have created ourselves just above here. And we'll get all of that things to a list. And eventually what's going to happen here is we can call that method on this following cell here and get an IEnumerable of image data. So just a list of images with the path to the image as well as the label that it has. So this is so far only normal C# code and has nothing to do with machine learning. From now on, we're going to dive in a little bit more into the intrinsics of ML.net. And the first thing being creating an ML context. In ML.net, everything resides around the ML context. And the ML context is somewhat like an EF Entity Framework DB context in that it has all the methods you can use to work with your machine learning model. So what we do here is to create an ML context, and from the ML context we can access methods from different catalogs, in this case a data catalog. And we can load all of our images from an enumerable into something called a data view. On the data view then, we can then shuffle all the rows to make sure that all our images are randomized. And we're doing this because we don't want all of our gene images or all of our pen images to come in a sequence, because that can inadvertently affect the performance of our machine learning model. We want them to be completely random, so we use a built-in function here to shuffle them. Following that, what we then do is we do some pre-processing on the images. And this is not so important for this talk, but what we're doing here is we are mapping our categories, which are textual values, right? It's genes or pens, right? We map them to a key, because our machine learning algorithm that we're going to use needs numeric values to better create a machine learning model. What we're also doing here is that we are taking all of our images and we're loading them into memory to a byte array. And all of this can be done using built-in machine learning or built-in methods in ML.net, such as appending a load raw image bytes transformer, as you can see right here. One of the many advantages to using something like Jupyter Notebooks to build our model is that we can leverage the data exploration power that this notebook has. We can import open source libraries such as Plotly, and we can create our own graphs to understand the distribution of our data. For example, in this case here, what we're doing is we're taking our shuffled data sets, our data view again, and we're getting all of the values in the label column. And remember, the label is the answer we're trying to predict, so this is going to be all the categories. And we're getting all the categories, and we are creating a normal histogram here from the Plotly library that we have imported earlier from one of the dependencies. And if we do that with a simple layout here with a title and just dump it to the console, what we'll end up having here is a nice distribution of what kind of types of images we have. So we can easily see here very interactively that we have 39 ties. We have the majority of the images being shirts, all 521 of them. We have about 99 jeans and so forth. What we normally want to do when we create something like this, which is a multi-class classifier, is that we want an even distribution of images. So the fact that we have 500 plus shirts is a little bit unfortunate, because what that will mean is that the model will be a little bit skewed to say that, yep, it's probably a shirt, because in most cases it's going to be a shirt. I think we'll be able to create a stable and robust model regardless, but that's something to take away for your own project going forward. Alright, so now we know the distribution of the data, we can go back into trying to build our machine learning model. The next step in building a machine learning model is going to be to split the data into a test and training data set. And we can use a train test split method on the data catalog in MLNet to do so for us automatically. By default, it will take about 90% of the images and split them into a train data set and save about 10% of the images for a validation set or a test set. You can override this method yourself and supply your own values for the splits, but for now I think this is going to be just fine. Once we have our test and a train data set, we can do the real magic here and create our data transformation pipeline, which will contain the multi-class classification trainer that we'll need to achieve this image classification task. And as you can see here, what we're doing is we are looking into the multi-class classification catalog in the ML context. We're picking a trainer, and a trainer is just another word for algorithm here in this world. And we are choosing to type image classification. And what we're doing here is we are supplying this image classification with a set of options. So remember, what we're doing here is transfer learning. We're not trying to build our own architecture of a deep neural network. We're not trying to define how many layers it has, or how many neurons in each layer, or which kind of activator or optimizer it has. All of this is going to be supplied for us, and we just need to tweak a couple of features and options to make sense. So in our case here, we have decided to use the ResNet v250 architecture for our computer vision task. And this network was initially developed by Microsoft. What we're saying here is that, yep, our feature that you need to input into this network is going to be the image. So what it's going to do is going to split up that image with the pixel values for different color channels and feed that into a network. What we then say is that please train this network by passing all the images with all the pixels in 5 different times. And each time what it will do is it will adjust the weights and biases within the network. For those layers it has unfrozen. And the batch size here is 10, which means that each time we pass, we adjust our weights and biases, we want to pass in 10 images. And this is so we don't just swing back and forth too much when it comes to adjusting weights and biases, so we actually have a nice distribution. Learning rate is very important when it comes to the gradient descent, and that has more to do with the optimizer on how we are adjusting our weights and biases. A smaller learning rate will mean that we'll probably find a minimum and really get to the bottom of the minimum, so an optimal model, but it will take a lot longer as well. If you have a larger value, we will most likely not find an optimal model, but we will probably get to minimum faster. So this is a little bit of trial and error, but if you don't want to supply this value, the default value that the library chooses is most likely going to be good for you. So remember, you don't need to supply all these values. A lot of these are supplied for you, but you can choose to override them if you want to. The last two values here are the metrics callback, and this is a way for the TensorFlow implementation under the surface to actually output the metrics for each of these epochs. And we're also supplying the test set. So for each of these epoch, we're going to allow TensorFlow to evaluate the performance of our model and output the accuracy and entropy. So once the pipeline is defined, we can then call the fit method on our training pipeline like this to start the training steps. So all of these things above here is going to be very quick because it's going to just load things into memory. It's not actually going to do much work. But when you call the fit method, we are calling the TensorFlow API under the surface, and TensorFlow is going to start to use transfer learning to retrain unfrozen layers. And what happens is that we will get this nice output in our console. The first step here is just going to be loading all the images into memory, and that's what it's doing right here with an image with an index for each image. But if you scroll far down here, we'll eventually go down the end here. We'll start doing some interesting things here. And since we only had 5 epochs, we're only going to have 5 lines. And for each epoch, you will see the same thing more or less. First thing we'll see here is that we have the 0.01 learning rate, right? Which is going to be affecting the gradient descent that is adjusting the weights and biases. The 0 epoch is the first epoch. In that case, we had a 0.98 in accuracy, which is a 98% accuracy. And we had a cross entropy of 0.12 here. And we want this cross entropy to be as low as possible, and we want this accuracy right here to be as high as possible. And we can see here during each epoch, we are increasing our accuracy, which is a good thing, and we are decreasing our cross entropy, which is also a good thing. So it looks like we're ending up with a more and more accurate model. And already after 5 epochs, we can see that we have a model that is 99.9% accurate, which I would say is fantastic. And what happens after that is that we are freezing 2 of the variables that we have decided to retrain, and we are saving our model to disk. After TensorFlow has finished training its model, what we then can do is take that model that has been trained, and we can evaluate the model based on a test dataset one more time. What we want to do here is we want to transform all of our test data and see what it suggests the category to be for each of those images. And what will happen here is that we'll create a predictions variable, and the predictions variable will have both data for the category it thinks this image belongs to, but also the score of that prediction. So remember that machine learning is not black and white, it's actually a gray zone. So we may have a prediction saying, this is a pen, but I am only 65% sure it's a pen, or so forth. And what we can do then is we can use those predictions to get metrics of how well our model is performing. And those metrics can then be plotted, for example, by using a confusion matrix. A confusion matrix is very, very useful if you're doing a binary classification or multi-class classification, because it allows you to get a nice insight into how your model is thinking. Is it, for example, confusing pens with jeans, or is it confusing paper with a shirt or something like that? And all that information will be useful for you, so you can augment your data or do other changes to more easily separate between classes. And again, what we can do here is use the open source library Plotly that we have imported earlier to plot a heat map here. And this heat map is going to more or less illustrate how our predicted values differentiate from the true values. If we do that real quick here, what we'll end up having is this schematic right here. In an ideal world, what we want to have is only red during the diagonal here, because on one side here we have the true values, and on the other diagonal we have the predicted values, and we want them to match. For example, we can see here that 8 of the ties are correctly predicted to be ties, and we have nothing in the column or in the tie row here that indicates otherwise. So there's no confusion about ties. Ties are simple to predict and they're easy. But we can see here for backpacks and socks that one backpack was confused with a sock. So there's something with the socks here that makes them look like a backpack, or vice versa. So knowing this, we may want to augment the backpacks or the socks, maybe take different pictures with different colors or different angles, so that our model maybe better at distinguishing between these two categories. And if the model is better to distinguish between these two categories, we will also get a much more accurate model, and maybe we'll increase it to 99.9 or even 100%. So to wrap this up, once we have validated our model and we have trained it, what we can then do is save it to disk. And we can do so by just calling mlcontextModel.save and supply the model as well as the schema and the name we want the model to be called. And in this case, it's going to be imageclassifier.zip. This zip file is going to contain all the information we need for our model, and if we want to use it in our application, we'll call a similar method called load and supply just a path to the model, and from there we can create a prediction engine and do predictions from our application, whether that is an Azure function, ASP.NET Core application, or something else. That's going to be completely up to your choosing. And with that, I want to thank you all so much for joining into this talk today. I hope it has inspired you to try out machine learning, and I hope you learned something new. Should you have any questions, don't hesitate to reach out to me on Twitter or on GitHub. I have a lot of examples, both using Jupyter notebooks, but also examples using Visual Studio Code and Visual Studio with ML.NET. Thank you.